So I will start with a few videos which I like, and I'm going to explain what's going on here. What you see on these different videos are different experimental platforms developed by VALEO, which are traveling across Europe, across the US, or driving in city centers, and you see different views of the vehicle, with the technical view at some point with the LiDAR points and the detection of the 3D objects, etc. So it was before COVID time, by the way. And what is remarkable about this vehicle, which are developed in another team at VALEO, and there is one representative in the room, if you want to discuss with Xavier Perroton, is that these platforms, they are fitted with the sensors, cameras, LiDARs, etc., which are commercial sensors. So they are already in individual cars, and they are used in this case to build more advanced systems of driving assistance and autonomous driving. So why do we care at VALEO and in the car industry or the mobile industry at large? Why do we care about ADAS and autonomous vehicle? The first obvious reason is to make the transport safer. There are way too many casualties on the roads every year in the world. But also it's to save time, hence my little note at the beginning of my presentation, and also to make transport more efficient in terms of energy, and also more inclusive for people who are excluded from efficient transport at the moment. So these are all good reasons. But when you think of it, it's a bit of a crazy idea to have these robots on wheels in cities. They are based on machine learning and deep neural networks, and we are going to talk about their limitations today. They have to run in real time on limited budget because it's embedded. They are, of course, extremely safety critical, and they have to be deployed in an open world which is fairly unpredictable, especially in city centers, but not only. And last but not least, as opposed to a mobile phone, these objects, they have to operate for more than 10 years in average, so there is another challenge there. Okay, so the challenges of what is called autonomy level 3 to 5, which are the different levels of automation where the car becomes in charge as opposed to the driver, either partially or completely at level 5, is that, as I was alluding to in the previous slide, that the system has to work in fairly diverse conditions. At level 5, it should be in all conditions. So different driving situations, from high-speed driving on highway all the way to low-speed maneuvers and traffic jam in very different regions of the world, and the different conditions of weather, illumination, etc. And it should be robust to all types of perturbations, degradation. So on the visuals here, what you see on the left is a well-known American car model being on so-called autonomous driving system and being completely nuts because of the sun glare, and it's so the way it keeps the lane is a bit worrying. Of course, you can have to face sometimes heavy fog, probably not in California. And what you see on the right is another example from Earth, where you have fisheye cameras, which are very low on the car and outside at the bumper, and it can get extremely dirty, as you can imagine. And still, these are some of the sensors that you have to use, say, for parking or for low-speed maneuvers. So what can we do in order to address all these challenges? And I will show a few things in my presentation along these lines, not on everything, but just to list things. The first thing is that you can use different sensors, which are complementary, and also to get more and more data, in particular for training, because machine learning at the moment is extremely data greedy, and this data can also be simulated. Also, this data can be, there are new ways to use this data, even if it's not annotated, and I will discuss that a bit as well. And at the end of the day, we also need probably stronger ways to test and validate the systems, either on track or on roads. Another aspect which is very important and very challenging when it comes to machine learning is to be able to estimate the uncertainty of the decision of your system. and also maybe to try and interpret better the decision, which is another challenge. And last but not least, these cars, they follow the law of physics, they have to respect rules, etc. And there is the behavior of the human users of the road, and there is a lot of knowledge that could be leveraged, ideally, in the system. The three examples that I show on the slide, on the top right, you see a point cloud which has been annotated using, so it's LiDAR point cloud, using AI in order to do better annotation of partially manually annotated data. You see on the left one of our data collection car in Ireland, and you see that it's fitted with quite a few sensors, including what we call reference sensors, like a 360-degree LiDAR on the top. And at the bottom right, you see an example of radar data, which I will elaborate a bit more later. Okay, let's start with sensors, because it's really, obviously, the input to these autonomous systems. And I will illustrate the diversity of the sensors, talking about the VALEO sensors, but they are certainly typical in their types. So you have the ultrasonics, you have the radar, the LiDAR, and the camera. So the LiDAR is the laser scanners. They come in different flavors, different range, different resolution, etc. And they can be fitted all around the car in order to perceive the surroundings at short or long distance. And what is interesting, of course, is that they sense the world in a very complementary way. A camera is a very rich, there is a very rich signal. It's pretty good to read signals, signs, for instance. LiDAR is good for 3D and not too perturbed by low illumination. And radar is another type of sensor that we like a lot. And I just wanted to focus a bit on the radar today. So what you see here is almost raw radar signal where displayed in different ways. So effectively, you have a cube of data with the angle, the range, and the Doppler effect, which is essentially the relative speed of the car with respect to the radar. And you can display that in different ways. So it's essentially the energy that you see here, the spectrum, with the trace of a car and signature of a car on a pedestrian. And it's not so easy to decipher for the human eye. So what thing we did in collaboration with Telecom Paris is to annotate such data in order to train model. And so this is a data set that we have publicly released, where we use the camera to align with the radar to detect automatically with off-the-shelf systems or models, cars, pedestrians, and cyclists, and then we can reproject that in the radar signal, and then we get almost automatically segmentation and detection of the road users in the radar signal. This is what you see on the right of the panel in the two different views of the radar signal. And with this data, then you can train a neural network, and this is the follow-up work we did with Telecom, where you start with this cube of energy, energy which you have at each instant, and from which you can extract different 2D views, either range, angle, etc. And then you can build and train a neural network with different streams and different heads in order to produce the semantic segmentations of two of the views, in this case, the range Doppler and the range angle. And just to confirm that these two segmented objects here are indeed a pedestrian and a cyclist in this scene. Another even more recent follow-up work here from the team is to use HD radar. So in this case, the angle resolution is much better because you have way more antenna in the radar, and we have released another data set called Radial, where you have the raw radar signal, but also the camera and the LiDAR, and you have these point clouds, and you can have the objects which are segmented in the annotation. So you see both the boxes for the cars, and you see the segmentation in green for the drivable area, which is obviously one of the objects of interest for the system. Okay, so moving on, with data, one of the challenges we face is that at least for state-of-the-art machine learning models, we need a lot of annotation, and notation is very costly and sometimes very difficult. I just showed the case of the radar. Annotating by hand radar is difficult. So one of the research topic we have in the community is how to be more sustainable when it comes to annotation. So imagine that you have a lot of raw data, which is fairly easy to collect. It's a bit bulky, but you can drive and collect things. But you have a limited budget for annotation. How to make the best use of this data? So now the mainstream or the very powerful way, which has been explored by the research community and is now very powerful, is to transfer the knowledge from data which is annotated to data which is not, so the transfer can be across different modalities, like different sensors, as we saw with the radar. It can be through different conditions. It can be through different models as well, different tasks, etc. So it's becoming very powerful. And there is a long list here of tools which I'm not going to go through in order to do that. And I will just show examples of domain adaptation today, and maybe if time permits, of self-supervised learning of representations. But there is another important way to get annotated data if you don't have the manual annotation budget, is to generate automatically new data. So you can, for instance, take real scenes that you change in order to simulate other conditions, or you can take real scenes and change to some extent the structure or the positioning of the objects. It's a bit more difficult. You can go the full simulation pipeline, which is something also very powerful nowadays, and many players in the field are going this way. But today I'd like to focus mostly on domain adaptation. So the problem here is how to fill the gap between the distribution that you see at train time and the distribution that you will see at deploy time, which is really a key problem. So in terms of terminology, we have data from what we call the source domain, which is quality data, annotated, etc. And you have also data not annotated of so-called target domain, which is supposed to be representative of what you will see when you deploy the system. And a very classic example of that, very important, is a simulation to real domain adaptation, where you have perfectly controlled synthetic data you want with full annotation, and you want to use that as much as possible to train your system, but also you have real data at train time. So, and in this situation, the domain gap is so large that it's quite classic to have dramatic drop of performance. So in this example, what you see, you will see in a second, is a semantic segmentation task where you want to annotate each pixel semantically. If you train on synthetic data and then you run on new synthetic scene, then you get fairly good results. But if you just transfer, well, if you just use the same model on real scenes, this is what you get, which is certainly less good. So this is exactly what we want to address. And unsupervised domain adaptation, it's called. This problem has been addressed a lot in the machine learning community over the years, but with the era of deep learning, it has become a branch of deep learning, in particular using adversarial domain adaptation. So the idea here is that because with deep learning you learn at the same time the final classifier or predictor, but also the features that you are going to work on. In this case, the idea is to learn features which are task relevant, but also which are domain independent or domain agnostic. And in order to do that with adversarial training, the idea is that which you have a model here, the main model in orange, that you can train with the classic way with this full supervision on the source domain data, and you're going to pick some level of representation in the model, either at the input, in the middle, or the output, close to the output, or throughout the model. And you are going to co-train a discriminator, whose task is to decide whether the features they come from source domain data or target domain data, and hopefully it will be confused in the end, which means that the features are indeed domain agnostic. And you do that with adversarial training, and then when you are done at deploy time, you just run your train model on data whose distribution is hopefully close to the blue data you had at train time, without annotation at train time. So, and it's something we've been working on in the past 3 years. Again, you see the same example where you see that if you train on synthetic data for semantic segmentation, on real data, the result is not too good. And what is we found interesting is to look at the confusion of the model at the pixel level using the entropy as an indicator. And you see on the two heat map at the bottom that on data similar to the source distribution, the model is only confused at the boundary of the objects, and on target data is confused all over the place. And this is something we have leveraged in our system. Then owing to the fact that we do have real images unannotated at train time, and we managed to use that in order to train the model such that it gets better and less confused when it sees real scenes, which is exactly the goal we had. So these are just qualitative examples, and you can find easily the videos and more examples on our webpage. Where I showed 2 examples of the improvement we get with the method we proposed, and on 2 classic benchmarks, and it translates into a few points of improvement in what we call the mean intersection over union metric, which is the classic metric for semantic segmentation. Another thing we can do is to leverage cross-modality, and this is a work in collaboration with INRIA, where we address a similar task, but this time it's semantic segmentation of the point cloud. And we figured that if you have both cameras and LiDAR, then you can address the same task, but the domain gap can be different in the 2 modalities. Typically, at night, whether it's day or night, the LiDAR sees the same structure essentially, whereas for the camera it's very different, and vice versa in different situations. So what we have put together here is the system where we train 2 models, one from images, one from point cloud, to address the same task, and they interact each other at train time, and we can use that in conjunction with domain adaptation. And just to show an example where the system has been adapted to day to night time images for which there is no annotation, whereas we have annotation in daytime. And you see here that on the left we have misdetections or false positives, which are fairly well corrected by this system on the right, which is called XMUDA for cross-modality unsupervised domain adaptation. Okay, another aspect which we found interesting in domain adaptation is to use a first version of the model in order to annotate automatically some of the target to the domain data, and then we retrain the model with this automatic annotation. But of course, this automatic annotation is noisy, and I'm not going to enter in the detail, and I'm going even to skip some slides. But what is key here is that we need to predict the confidence or the uncertainty of the model to make sure we select the right pixels or the right images to do the retraining, and it does work. Let me just skip for sake of time, and I will share those slides anyway. Just to emphasize here one thing. So what I just said is that we need to assess the confidence of the neural network in its prediction, and this is in the case of domain adaptation, where you want to annotate automatically, but it's a very important topic at large. So if you think in terms of the model itself, being able to assess the confidence allows you to predict the failures or likely failures, even maybe to reject the input because it's an out-of-distribution input, or, as I just said, to select automatically labeled samples, or even it can be useful in reinforcement learning. But if you think in terms of complete autonomous systems, having the uncertainty measures which are reliable allows you, in particular if the system, one part of the system is very uncertain, you can inform the downstream tasks about the uncertainty or the next time step if it's a sequential system. You can also then attend to other sensors for which the output is more confident, or you can even, it's very important for autonomous driving, go to the fallback function, or you disengage the autonomous driving system, just giving back the hand to the driver. And one way to address this prediction of the uncertainty that we've been working on is to train another neural network, so as it were an auxiliary model, which is in charge of predicting or in charge of monitoring the main model. So, so you have your main model here, which predict pseudo probabilities for classes in case of classification. It's been trained, so it's frozen now. And we train another model on top of it, which sees the features, the inside features of the main model, and it's trained the following way. It's trained in order to predict what is the score of the true class. And at train time, we, at least in full supervision, we have the true class. And then at runtime, this auxiliary model, confidence, we call it ConfidNet, will be able to predict to some extent the confidence of the prediction of the main model, capital F. All right, I don't know how much time I have left, 5 minutes, that's good. I just wanted to finish by alluding to a very important topic in the, let's say, autonomous driving community at large, but in the all AI community, which is self-supervised learning. So this is the idea that you just tap into unannotated data at a large scale, and you learn representations which are going to be useful for other tasks later on. This is a topic that we have decided to investigate in the team quite recently, in particular with the angle of the cross-modality. So we leverage the fact that we have aligned LiDARs and cameras, and these two modalities, they can sort of crosstalk, and this allows to define automatically what is called pretext tasks in order to learn representations. So we have two work, which I will just show quick videos, not explanations. But in one case, the task is to do semantic segmentation of the LiDAR point cloud, and we use the visual modality in order to define interesting tasks to be learned, and vice versa. In the other work on the right, we address semantic segmentation of the image, and we leverage point clouds which are automatically segmented or clustered in order to define interesting tasks to learn for this. Let me just skip. Yeah, I just want to show that in order to keep time at the end. So in this is the second work I wanted to mention, which will be presented in 2 weeks at ECCV. So what you see on the left are the images from the camera with the point cloud superimposed in color for the distance. And with our system, we get a fully self-supervised semantic segmentation. Maybe semantic is a bit of, it's not the right word, but full segmentation of the scene, and you have to keep in mind that the system has never ever seen a semantic label of a pixel in the training, and it turns out that these segments on the right can be then used as pre-annotation, and they can be fairly easily matched to actual semantic classes, and this is something that we find very promising. All right. Just one example where you see that in this case, what you see in the middle is the result after matching with the actual semantic labels. So that's why on the right you see the ground truth, and you see that the segmentation again is fairly good, especially on top of that, in this case, the results are on bad weather or nighttime images, whereas the training, fully unsupervised training, has been done only on daytime in this example. So it means also that it does transfer pretty well across domains. All right, in order to conclude this short presentation, I think one of the big challenges we have with the systems, and it does extend to other applications, is that we need a lot of robustness across a large variety of domains of operations, and it's in particular in the case of vision-based systems, it's very challenging. And no matter how hard we work, we will lack anyway real data to cover everything. So in order to address that, there are a few tools that I have highlighted today. One is to have a good suite of complementary sensors. Another one is to use cutting-edge techniques in domain adaptation. Self-supervised learning of representation that I just illustrated is certainly a good thing to do, in particular when you have different senses at hand, and predicting uncertainty is certainly important as well. And the last note is also to mention the fact that, at least for the assisted and autonomous driving systems, looking at the driver as well is very important for obvious reasons, and this is now a call for the community. We do miss big, good data sets for that, whereas we have now a large offer of data sets for external perception, so I think we should collectively look at that. And with that, I will just show the team, and you have all the links to the different materials at the bottom of the slide. Thank you very much.
Thank you, Patrick. We may have time for one or two questions. I take advantage of being here to ask you the 1 trillion euros question.
The worst questions.
So, when do you think all this will be trustworthy enough to be put in large scale on the road?
Somebody had to ask. So I think if we really talk about fully autonomous cars, driverless, no pedals, no wheels, it's not clear it will happen, at least for the privately owned vehicles. But it already happens for shuttles to some extent, and robotaxis, which are very high-end vehicles. So this is still experimental. The services are tested in several parts of the world. What is clear is that advancing the level of automation in assisted system like ADAS is progressing every year. So we had the announcement this year of Mercedes and Honda cars with automation on highway up to 60 kilometers per hour, using, among other things, our LiDARs. And these are realities now. These are commercial models, but they are not driverless cars. They are cars with an increased level of automation. So I think it's also important to see the continuum from ADAS to fully autonomous driving.
I don't see much because of the lights here, but are they? Yeah, there's one question. Are there microphones for the room or no? I have to give you.
Can you repeat the question otherwise?
No, someone's coming.
You have a message to define confidence in one of the slides.
Yes.
And if you use the neural network also to estimate this confidence, then you may have also a problem with systematic errors. How do you overcome this?
Okay, that's a good question. So now we need to predict the confidence of the confidence network. No, that's certainly a challenge. It's already hard to train this network because we need, if the model that you want to monitor is too good, we lack examples of failure. So we have very imbalanced training data. So it's in a sense it's not magical, but at least it's the message here is that there are now fairly simple ways to at least monitor the features of your main model to decide, well, to indicate that maybe something is not right, or the input is really far away from the distribution that the main model is able to handle. But I think at the end of the day, this will need to be coupled with other systems, including explanation systems or other systems which are with different architectures, etc. So to me, it's just the beginning. It's one attempt to do that, but we are really at the start of this type of studies, I think.
Yes, I have a question regarding the adversarial domain adaptation. So do you think it would be possible to learn a domain agnostic representation for just one source domain by generating a family of transformation applied to the color palette to generate synthetic target domains and do your adversary training upon that in such a way that if you have just a few data from an actual target domain, it will be easier to adapt.
So this already exists. So this type of on-the-fly domain adaptation, leveraging only one small part of the model, which is designed for that. It's called, sometimes it's called modulation, etc. You can change the statistics of the for instance, the batch normalization. So there are ways to tune or to adapt an already trained model on new distribution. And it's also connected to not so much domain adaptation, which is at train time, but domain generalization. So you either adapt at test time, or you even ideally you have a model which has learned so much invariance at train time without losing accuracy for the task that it can really now go and see other different, though related domain, of course. But I mean, there are different scenarios in domain adaptation, in domain generalization, on-the-fly domain adaptation, and I think so. The literature is pretty vast, and it's a very active field of research. So we can take it offline if you wish.
So I don't see any other urgent question. It seems. Patrick, are you going to stay for some time?
I have to say no, because I have to run now. But I will definitely be reachable by email. Thank you very much.
Thank you again, Patrick.